Hello everybody, and welcome to the start of Chapter 14 in the workbook. We're looking at page 29 here. And the topic of this chapter is of this section is partial derivatives. We're going to start a discussion of finding the rate of change of multivariable functions. To get us started, we have an example to kind of lead us into this concept, so let's read a part of this together. So we're given the temperature capital T in degrees Celsius at a point xy on an 8x8 metal plate. That's what we're seeing in the picture here, down here. The function we're going to call t equals f of xy. That's our temperature function. We've got inputs of x and y and then output of temperature. Okay, and x and y, these positions on the plate, are being measured in meters. Okay, then notice that we're given this function in two forms. There's a table of values that actually tells us the temperature at various places, and then we've got a graph. Okay, and that gives us the same information just graphically, showing us where the temperature is. Okay, and in this problem, our general goal here is to kind of describe how might we find the rate at which the temperature of the plate changes. Okay, before we dive into this, let's maybe think qualitatively about the problem as a whole here. So, based on the information that we have, can you see where the temperature on the plate would be the highest? Where is the highest temperature occurring? Okay, you could either try to answer this question using the table or the graph. I'm going to look over here to the right at the graph. So the biggest temperature should be where the graph comes to the highest point, because temperature is on the vertical axis. So maybe somewhere in the vicinity of here, and notice that that happens kind of near the center of the plate. That appears to be where we're getting the greatest temperature. Okay, so all of that said, let's get started thinking about the problem of rates of change of temperature. First thing we need to do is to talk about notation. How do we write down the rate of change of temperature? Okay, well, there's kind of some special notation for that. Okay, if you haven't seen this before, this might look a little unusual at first. Okay, so suppose that we wanted to measure the rate at which the temperature changes in the x direction. The way that we write that down is this. In words, we would read this partial t, partial x. I'm going to write that partial t, partial x. This strange little symbol that you see here that looks like a 2 is read partial, and it represents derivative. Okay, so in words, this is the rate of change of the temperature T with respect to x. Okay, and when we think about this rate of change, we are holding the other variable constant. Okay, we're only thinking about moving in the x direction along the plate, and in a minute we'll talk about how we might get a number for that. Okay, and then similarly, if we want to talk about the rate that the temperature changes in the y direction, we're talking about partial t, partial y. Okay, and in this case, we'd be holding x constant. All right, well, again, how would we find numbers for these? Well, let's pick a specific point that we want to that we want to do this at. I'm just going to pick anything. So how about the point 3, -1? Derivative at 3, -1. See if we can measure the two rates of change that we wrote down above at that specific point. So first, let's find the point 3, -1 in our table. So here's x equals 3, y equals -1. So we'd be talking about this point. Okay, right at that point, the temperature is 50, and we're asking how fast is the temperature changing in these two directions. Let's start with the x direction. Okay, so in symbols, partial t partial x, again, that's the rate of change of temperature in the x direction at the point 3, -1, would be, okay, before we calculate it, let's see if we can figure out whether that rate of change is positive or negative. So if we move in the x direction, we're talking about moving left to right. So we'd be kind of looking at 55, 50, 43 as we move in the x direction. Notice that those temperatures are decreasing as we go left to right, so we would expect a negative derivative here. And to estimate a value, we're really looking for the change in temperature over the change in x. Okay, and to get the specific numbers, I'm going to just pick one point on either side. So we'll pick on the 55 and the 43 points that we see there. So the change in temperature would be 43 minus 55. And then we'd ask, how much does x change? Okay, we went from 2 to 4, so we're going to get a change of x of 4 minus 2. Okay, if you do the arithmetic there, 43 minus 55 over 4 minus 2, you're going to get -6, it looks like. And then the question is, what units would we have here? Okay, well, you can answer that question by asking what are the units in the numerator and the denominator. We're talking about temperature in the top and position in the bottom, so we're going to get degrees Celsius per meter. Okay, and actually, instead of saying equals here, I should say is approximately equal to. Okay, because we'll see in a minute why this is just an approximation. Okay, so there's the approximate rate of change of temperature in the x direction. It's decreasing. Okay, the temperature is decreasing. And what about in the y direction? How would this look there? Okay, well, partial t partial y, that's our notation for the rate of change in the y direction. This time, we can approximate that by taking the change in t over the change in y. Okay, and moving in the y direction means that we would be going this way in our table. Okay, so from 47 to 50 to 51, notice that this time the temperatures are increasing, so we'd expect to get a positive number, and to estimate it, we can pick a couple of points on either side of 50 and measure delta t over delta y. So let's see, 51 minus 47, that's how much temperature change we're getting. And then we went from -2 to 0, so 0 minus -2 is how much y changed. Okay, do the arithmetic there, and you're going to get +2, and again, the units are going to be degrees Celsius per meter. Okay, that's our approximate rate of change of the temperature in the y direction. Okay, now I want to think about this graphically as well. You might remember from Calculus 1 that finding derivatives is about finding slopes of tangent lines. Okay, these two numbers that we came up with also represent slopes. Okay, if we go back to our picture for a minute at the top of the page here, the point 3, -1 is sitting down here. Okay, and I'm going to go up and find the point on the surface. Okay, so the t value of that we already know from the table is 50. This slope in the x direction that we just came up with, you can think of that as the slope of this line. Notice that that line is kind of, it points in the same direction as the x-axis, and as you move in the direction of the x-axis, you're going from the back of the picture to the front. Notice that we're going down. Okay, our t values are getting smaller. That's consistent with the -6 that we got. Okay, so I'm going to label that line L1, and the -6 is the approximate slope of L1. Okay, you can think of it as the tangent line that kind of goes with this rate of change in the x direction. And then similarly, the 2 degrees that you found in the y direction, that's the approximate slope of L2, this line, that moves in the direction of the y-axis. And you can see that that line goes up a little bit as we go left to right on our picture. Okay, so there's a brief preview to the idea of finding rates of change, and in the next example we'll kind of tie some of the notation together.